This is the fifth part of Module 5. In the previous lecture, we discussed the operation of a current source inverter for the induction motor drive. In this lecture also, we will be discussing the continuation of CSI for the induction motor drives. As we know, a current source inverter consists of a voltage source in series with an inductance. In this case, a voltage source means a three-phase AC supply and a control rectifier, and it is having an inductance, a large inductance in series. So since we have a large inductance in series with the voltage source, it behaves like a current source. That's why it is known as a current source inverter. In some cases, the input supply will be DC. So if the input supply is DC, instead of using control rectifier, we can use a chopper. So a DC supply, a chopper and a series inductance will give a current source. So now we are going to replace this entire system with a current source like this. So here, this is the current source and this is the inverter. And as we discussed in the previous lecture, we have 6 thyristors T1 to T6 and a combination of 6 capacitors and 6 diodes for proper commutation of the thyristors. And in this figure, we have the current profile of one of the phase currents, this IA. One of the phase currents IA is plotted here. So as we know, for a current source inverter, the thyristors are triggered in the order of their names with a phase difference of 60 degree. That means when T1 is triggered, then after 60 degrees, then T2 will be triggered. In that manner, all the 6 thyristors are triggered, and a combination of 2 thyristors, for example T1 and T2, simultaneously they will operate or conduct for 60 degrees, but a single thyristor will conduct for 120 degrees. And since we can see the current profile in this picture, the current suddenly rises and falls. This is a speciality of the current profile of a current source inverter. And if we write the equation for the stator current of this induction motor, this is the stator of the induction motor. So if we write the equation for the stator current of the induction motor with the help of Fourier series, the fundamental component of RMS motor phase current can be obtained as Is is equal to root 6 by pi Id. From this equation, we can say that for a given speed, the torque can be controlled by varying the DC link current. By controlling the DC link current, the torque can be controlled by changing the value of Vd. Vd means the DC link voltage of the input voltage source. Now, as we discussed, if the supply voltage is AC, then we have to use a fully controlled rectifier between the supply and the inverter. This is the DC link voltage Vd. And if the supply voltage is DC, then we have to use a chopper like this. DC supply, chopper and CSI. Now, for both fully controlled rectifier as well as chopper, the control should be such that the maximum value of DC output voltage, the maximum possible DC output voltage of the chopper as well as the control rectifier should be chosen such that the motor terminal voltage saturates at rated value. That means the maximum possible value of the full converter and the chopper should be selected such that the motor terminal, the maximum value of motor terminal voltage should be equal to its rated value, rated voltage. A voltage which is greater than the rated voltage of the motor should not be injected to the induction motor. This case we had already discussed in the previous lecture. Next, we will discuss some of the features of the CSI fed induction motor drive. First one is reliability. We know that we have 6 thyristors in the inverter. So if any 2 thyristors of the same leg, for example in the first leg we have T1 and T4. So if any 2 thyristors of the same leg conduct at the same time or simultaneously due to the commutation failure of any of these 2 thyristors, then there is a chance of short circuit. If it is in the case of a voltage source inverter, then it may cause severe damage to the system. But in the case of a current source inverter, since there is a series inductance in the source side, a short circuit current, the damage due to the short circuit will be prevented. So the system is more reliable as compared to voltage source inverter. In the case of voltage source inverter, in order to prevent the short circuit or in a sudden increase in current, we have to provide expensive fuses. But for CSI, it is not required. Next one is large voltage spikes. As you know, the current profile of a current source inverter indicates sudden increase and decrease of currents. So this sudden increase and decrease of current happens through the leakage reactance of the motor. So if we are using a machine with high leakage reactance, then it may cause high or large voltage spikes in the system. So in order to avoid this, we have to use machines with low leakage reactance. Then next one is expensive. As we know, there is a large inductance in the source side and 6 capacitors are to be provided for proper commutation. So due to all these things, the system becomes very much expensive. Then another thing is more weight and volume. As we know, in order to prevent the voltage spikes in the system, we have to use machine with low leakage reactance, but only using a machine with low leakage reactance is not enough, but we have to use capacitors with high value. Large capacitors are to be used to prevent voltage spikes. So the entire machine becomes more heavy and bulky due to the presence of this inductance and large inductance capacitances. Next, the regenerative braking and multi-quadrant operation of a CSI fed induction motor drive. So now we will discuss how the CSI fed drive operates in all the 4 quadrants. First, the operations are almost similar to that of a VSI fed induction motor drive. So in order to bring the machine to the second quadrant, then we have to reduce the inverter frequency. So when inverter frequency is reduced to make synchronous speed less than the motor speed, the machine works as a generator. That means power flows in the negative direction. So power flows from machine to DC link. And at the same time, DC link voltage reverses. Here also we have to consider the 2 cases. Either the mesh supply may be AC or it may be DC. If the supply voltage is AC, we will be using control rectifier, and if the supply voltage is DC, we will be using chopper. If a fully controlled converter is made to work as an inverter, then the power supplied to DC link will be transferred to AC supply and regenerative braking will take place. That is one option. Then next thing is, in this case, no additional equipment is required for regenerative braking of CSI fed induction motor drive with fully controlled converter. Then, as we discussed in the VSI fed drive, changing the phase sequence of CSI fed inverter control of induction motor will provide motoring and braking operation in the reverse direction, that is third and fourth quadrants. And let's consider the case of a chopper fed inverter. The drive using chopper can have a regenerative braking capability and 4-quadrant operation if a 2-quadrant chopper providing current in one direction but voltage in both the directions is used. So this is the possibility of using a chopper. If the supply voltage is DC, you have to use a chopper. So that chopper should be a 2-quadrant chopper which provides current in one direction but voltage in both the directions. Then we can implement regenerative braking. Next is this closed loop speed control of CSI fed drive. It resembles the VSI fed, that is voltage source inverter fed drive. Similar to that, it is also having an inner slip speed loop and outer speed loop. When the speed of the motor is sensed, it is compared with the reference speed and the speed error is given to the speed controller. The speed controller is normally a PI controller. The output of the speed controller is given to the slip regulator. The slip regulator always saturates at the maximum possible current of the drive, and the output of the slip regulator is the reference value of slip speed. Slip speed is nothing but the difference between synchronous speed and actual speed of rotor, that is omega ms minus omega m is equal to omega sl. So slip speed, the reference value slip speed is added with the actual value speed, that will give the synchronous speed. So this value of synchronous speed corresponds to the desired frequency of operation of the inverter. So inverter will be operating at a frequency that corresponds to this omega ms. So frequency of the inverter is adjusted according to the desired value of speed. Now let's consider this loop. Here we have a flux control loop. So let's see what is the function of this flux control loop. As we discussed in the previous lecture, we have to maintain the flux constant up to base speed. For that purpose, that means the machine should be operated at rated flux or constant flux. For that purpose, we have to maintain a relation between the stator current and rotor frequency, or simply slip speed. And this is the relation. This relation should be maintained below base speed. So constant flux operation below base speed is obtained when the slip speed and the inverter current IS have the relationship as shown. This was mentioned in the previous lecture. So in order to maintain this relation, the slip speed, reference value slip speed is given as an input of flux control loop. So flux control loop will adjust or produce a reference value of ID star such that the flux will be maintained constant up to base speed, and above base speed flux will vary. So we have to keep in mind that up to base speed the voltage will be increasing, and when it reaches base speed the voltage also reaches rated voltage, and above base speed operations the voltage will be maintained constant only the frequency will be varied. Same as the case of a voltage source inverter. So we know that below base speed operation is known as constant torque operation because flux is maintained constant, and for above base speed operations, since flux is also varying, it is not a constant torque operation but constant power operation is achieved for above base speed operation. So as we discussed, we have the reference value of ID star. It is compared with the actual value of ID, DC link current, and the current controller and firing circuit will help to control the value of ID such that constant flux is maintained. This is how the closed loop control of a speed control of a CSI induction motor drive happens. And if we have to increase the speed of the drive, then we should give a higher value of omega m star, so reference speed. So if we give a large value of reference speed, then the speed error will be positive. That is omega m star minus omega m will be positive. So due to the positive value speed error, the slip regulator will give an output value of slip speed such that the motor will have to accelerate at its maximum possible current for good, fast response, and at the same time the flux will be maintained constant. And if you have to reduce the speed of the motor, then you have to give a smaller value of omega m star. So omega m star minus omega m, it will give a negative slip speed. So the machine will decelerate. Then the deceleration is deceleration happens when the machine operates as a generator, and during after deceleration, when it reaches the desired speed, that means omega m star minus omega m will be equal to 0. Then the machine will run at its at that particular speed, the final speed. Next, we will have a comparison of current source inverter and voltage source inverter. Most of the points were already discussed, so we will just mention all the points. First point is current source inverter is more reliable because the conduction of two devices in the same leg does not short circuit the input supply. This is due to the presence of the inductance in series with the system. But in the case of a voltage source inverter, the conduction of two devices may cause short circuit of the input supply, so it may damage the system. Next point is rise of voltage is prevented because of the presence of large inductance. That is, sudden increase in increase in current is prevented due to the presence of large inductance. But if we have to prevent increase in current in VSI, we have to provide high speed semiconductor fuses, which are very expensive. And third point is motor current rise and fall are very fast, that as we have already seen the current profile, very fast, and that creates high voltage across the windings, high voltage spikes across the windings. But in the case of VSI, no such problems will arise. Next, these high voltage spikes are controlled by having a large value of commutating capacitors, which may increase the cost and size of the inverter. But VSI is less costly. Next is slow response due to large value of input inductance. But in the case of VSI, fast dynamic response is possible. if VSI uses PWM inverter. If a six-step inverter is used, then response becomes slower like CSI drives. But in most of the drives, we can use a PWM for good response. Then sixth point is frequency range of CSI is lower than VSI. Hence, CSI drives has lower speed range. But frequency range is wide, and hence speed range is also wide. Next point, CSI requires a separate rectifier and inverter combination. As we know, in the circuit diagram we have a fully controlled rectifier at the beginning and then an inverter. Hence it is not suitable for multi-motor drives. But in the case of VSI, a single rectifier can be used to feed many voltage source inverters. A single rectifier and output of that rectifier can be connected to multiple voltage source inverter. Hence, we can use multi-motor drives. That is, it can be used to drive multiple motors at the same time. Then, regenerative braking is naturally possible in current source inverter, as we discussed in the previous section. An additional full converter is required to achieve regenerative braking in the case of VSI. Then ninth point is, if input AC supply fails, then electric braking is not possible in current source inverter. But in the case of voltage source inverter, VSI can use dynamic braking in case input AC supply fails. Thank you.